Hi there, my name is Tamid Rahim, and over the past few days, I set out to answer a very practical question. Can AI coding agents meaningfully contribute inside a massive, mature, brownfield code base, and not just create these cool MVPs, these cool greenfield MVPs you see everywhere? So, to test this out, I decided to contribute to PyTorch. And let's go a bit about why, right? So PyTorch, let's think about the scale. It powers some of the world's largest AI workloads, right? So basically, it's way over 1 million lines of code, and if you can safely contribute here, honestly, you can contribute in any code base, right? Second thing about the architecture, it's a very layered architecture with a Python front end, a C++ back end. We'll go a bit about more into architecture in the next slide, but essentially it forces you to really go through and understand a code base, a complex code base before making any changes, right? And yeah, so let's go into the code base architecture for that. So one of the biggest lessons that we learned is basically AI agents fail in brownfield code bases unless you really give them a map of the ecosystem. You really truly, you yourself understand how it works, so you can communicate that and guardrail off the agent properly. So before writing any code, I had to deeply understand PyTorch's architecture and extract patterns the agent must follow, right? So here's a bit about the high-level structure. So PyTorch is essentially a Python front end. So where the optimizers, modules, and utilities, and honestly, both of my PRs features are basically live here, right? And it has a C++ backend. This handles all the tensor ops, the dispatcher, uh, device routing, and so forth, right? I don't really have the agents modify this layer, but we still need to give them a level of understanding so they can understand how, like, essentially the Python calls flow towards that. So yeah. And finally, you have a autograd engine. This builds the computation graph and does all the gradient computation. Right. Again, we're not really touching the code here, but we still need to bring in awareness to the agent about how about the we need to be aware of autograd behavior so it doesn't really break gradient flow, for example. So the first feature is essentially LAMP, or layer-wise adaptive large batch optimization. So what's the problem that we're addressing? Large batch training breaks Atom. LAMP fixes this by using layer-wise trust ratios. From an agent perspective, LAMP is an ideal test case. It's mathematically complex, which, as you know, agents aren't the best at. Touches state management, works with parameter groups, and uses for each optimizations. And also, it must follow the already established optimizer conventions in PyTorch. So let's go through a little bit about the algorithm itself. So the algorithm is the exact same as Atom, which is already in PyTorch for the first steps. And then all we're doing is essentially computing this trust ratio. Um, the norm of the parameter is divided by the norm of the update to essentially scale updates per layer. This forced the agent to reason across multiple layers for numerical logic and PyTorch's optimizer API. So just to go a bit into the implementation, the key aspects of the optimizer design itself. LAMP is built by extending PyTorch's existing optimizer class. Of course, that means the agent doesn't have to write everything from scratch, but we still need to help it understand the current framework, the optimizer framework, so that it didn't, I don't know, essentially create something uh, which is not in line with the current practices for PyTorch, right? For the hyperparameter validation, is basically no weird values allowed. It just makes sure it checks for that. Prevents bad inputs that could potentially break training. For state initialization, essentially it's just setting up the internal memory correctly so LAM works. And yeah, that's basically the core tenets of the implementation for our LAM implementation in PyTorch. So for my second PR, I decided to take on essentially native model summary. So PyTorch lacks a native model summary, and people usually get by installing third-party packages. And honestly, this is a great test for agent-driven brownfield work. This requires hook systems, forward passes, parameter accounting, shape inference, and of course clean formatting, right? So it's great to showcase what it can do. So for me, for this PR, I kind of wanted to prioritize maybe increasing my odds of getting this PR accepted. And what we were essentially showing off is essentially an MVP. So we're excluding a lot of metrics, memory usage, and so forth, and really focusing down on the core output. It's the most relevant information you can get out of it, right? So for the implementation approach, for the hook patterns, I had the agent copy existing ones called, for example, module tracker, and we use forward hooks for shape capture. We and Yeah, we implemented some hook cleanup process, and yeah. So let's go into the output itself now. So here's what the model summary utility produces with a single call. PyTorch prints a clean, structured breakdown of your entire model. You can see each layer, its output shape. It makes it very easy to verify architectural decisions, right? And what's most important here is that this output format matches PyTorch's internal style and conventions. That means, yeah, AI agents can generate this code safely without introducing new patterns or breaking existing ones. And on the user side, it brings a very familiar Keras style experience directly into the PyTorch core. So key learnings from here are the main takeaways. So agents really need pattern libraries, not just instructions. They write correct code when they're given great templates, right? For the Lambda, it was the optimizer template, and for the code summary, it was essentially what was it? The hook templates, right? Code navigation is everything. Agents fail when they don't understand where a feature fits in the architecture. Scoping for MVP, very important. You got to guardrail them in. Can't really let agents overbuild and get into different files, which always going to be a mess. And yeah, test, right? Make sure you create the right tests, and the tests are passing before you're uploading it, before you're pushing your code. And yeah, that's basically my key learnings and my experience so far with contributing to open source using AI agents. Thank you very much for your time. If you have any questions, feel free to reach out to me at tommy.rahim@gmail.com. Thank you.